Data science is one of the most popular domain, but why it's getting the popularity and why all the companies are trying to use the data science themselves? Let me give you the example. Because all the companies are trying to use their data and getting the insights from them. So they want to use the data science technique. To keep that in our mind, we came up with the tutorial that is data science in 60 minutes. Before start the tutorial, let me introduce that Great Learning has came up with a brilliant idea that is Great Learning Academy, where you will get almost 80 plus free courses, and after complete your course, you can claim your certificate as well. And if you want to do these courses in your mobile application, that is also possible using Great Learning app.
Okay, get started. My name is Karthik. I work for a company called Latent View Analytics. My background has been a lot on the data management side of things, data warehousing, business intelligence for many years. I moved to kind of analytics, to Latent View a year and a half back, but has been on analytics for probably 3-4 years now, right? Doing some hardcore advanced analytics, machine learning kind of stuff. So what I would like to do today, right? I'm sure you guys would have heard a lot of things. I heard there was a logistic regression thing which happened, the time series forecasting. I'm sure you're getting a lot of different inputs in multiple ways, right? And in some sense, that's really I would say the problem with data science and machine learning and advanced analytics is that there are just a lot of moving parts, a lot of different things that are happening, right? So what I'm going to talk to you today is more like it's like a personal journey of sorts in terms of when you start getting a lot of this information, right? How to really segregate it in some way so that you can navigate through this space, right? And I say a personal journey because I was terribly confused, right? You learn some stuff, you learn specific algorithms and things like that, but how do you kind of slot it in some way so that you can basically say, okay, I know this, right? And you also have a feel in terms of what you don't know, right? In terms of you know what you don't know, right? That's extremely important as you kind of move through this space because, as I said, it's fascinating in its own way because there are a lot of different applications, a lot of different ways you can use it. But unless you slot it in some way, and I'm talking about just the math part of the whole thing. So the focus of this discussion is going to be on the techniques, right? The quantitative techniques. We'll just touch upon all the other aspects of business and things like that a little bit, but the core focus is going to be on the math and the algorithm part of it. Don't worry if you hear terms which you don't understand because jargons is part of life in almost in every discipline and data science is no different, right? You hear a lot of jargons, a lot of different algorithm names and stuff like that. But the real essence, the takeaway that I want you guys to take away from this session is essentially that you need to develop a personal map, right, in your own way as you go through this course and even beyond this course of saying these are all the different aspects of data science and machine learning, advanced analytics, whatever you want to call it. And for certain types of problems, certain things are applicable and what are some of the things that probably you need to gain more information on, right? So that's essentially the bottom line. And what I'm going to discuss today is my own way of organizing the different areas within this space, right? I'm going to divide it, I've divided into kind of 10+1 categories, which I will discuss specifically on what those categories are. But of course, there is jargon, there are things which you probably might not have heard about it earlier, but don't worry about it. That's really not the essence of the whole thing. Okay, let's get started. So the topic is navigating the data science world. Just a little bit preamble on why it is so fascinating, interesting, and why it makes sense for you to invest the time and energy to learn about different aspects of data science, which in some sense is preaching to the choir because you guys have already, as part of a course, you have invested extra time and you had the motivation to come and listen to somebody speak. So in some sense, you guys are already interested in this area. But the bottom line is, it is a fascinating area because the amount of data is increasing, and that's an inevitable truth, right? And why is it increasing? It's basically because the number of transactions are exponentially growing. There are a lot of interactions that are happening, the social media, the reviews on e-commerce websites and all that, a lot of interactions. And the other big chunk is observations, right? Sensors, kind of giving out a whole lot of data. And almost every single machine that is getting replaced is instrumented with a sensor, which collects a lot of information, right? And we are seeing all this in our daily lives in terms of how there is really data sloshing all over the place within enterprises and outside of enterprises. And somebody has to make sense of all this data for you to drive business decisions or society related decisions as such, right? Governmental decisions and stuff. So it is accelerating a digital shift, which we all experiencing in our own way. And ultimately there is a data deluge. There are different types of data, and I'm not talking just structured data. We are talking unstructured data, semi-structured data, all different types of data that's basically are out there. But interestingly, what's happening is, of course, it's unlocking a whole lot of newer use cases. So this is again from the vantage point of a latent view, right? We see a lot of different companies using data in many different ways. An automobile company trying to use sensor data to detect driving patterns, right? Once you detect driving patterns, you can have better warranty claims, right? There are companies out there which are trying to use social data to identify trends in the marketplace, right? CPG companies, fashion trends, because there's so much of information that is out there in the social space. There are companies trying to use, they've been using structured data, like say movie companies trying to do box office forecasting, right? They've been doing it for quite a while, but now with extra data coming in from social space, they can do better forecasting, right? So there are multiple use cases happening across the space: customer intelligence, marketing intelligence, sales intelligence, supply chain. Supply chain is a classic case of people instrumenting their assembly lines, getting all that data and trying to figure out, can I predict something in the assembly line, right? Can I predict when a failure could happen? Can I predict whether this assembly line throughput will reduce, right? So that I can take decisions accordingly. And that's for real. So I can assure you that these are things, you might have again seen it in your own work life, but if you haven't, take it from me that these are problems solved by organizations, and we're only scratching the surface at this point in time, right? And the interesting thing I'm coming to is the fact that yes, there were always a need for using data to solve business problems and all that, but now there is an increase in technology power, which is actually making it possible, right? You guys might have heard of this whole neural networks thing, which started in 90s, kind of, it just trailed off, right? Because there is not enough computing power. Or artificial intelligence. If you want to look at, some of this is fascinating, right? So stochastic optimization, which is the basis for many of these machine learning algorithms, is a 1953 paper. It's an 8-page paper which everybody goes back and refers if they want to really look at optimization. So it's not, these ideas are not new. It is just that now you have the ability to implement it in a practical context. Why? Because of the cloud, because of big data, because of the whole sophistication of algorithms and the tech power that is coming in. So new use cases, the tech power, all coming together, helping to solve different kinds of business problems. And the digital shift and the data deluge is a fundamental change, right? So it is worth investing the time to learn all this, because it's a journey, right? Each one of you are trying to invest time and moving in this direction. I think it's well worth it, right? That's the idea of this slide, right? So what does it take to provide actionable analytics? The way we see it at a very high level is about bringing these 4 elements together. Every single problem that you will try and solve in analytics essentially is a combination of 4 things at the end of the day, right? The sophistication might be higher, lower, proportions might vary, but it is all about bringing business, data, math, and technology together, right? I'll just repeat this. So the business part is about understanding what is the business impact, right, of doing something with data, of kind of running this algorithm or trying to implement a certain statistical technique. There's a data part of it, structured, unstructured, semi-structured data. How do I understand it, right? How do I make sense out of it? How do I explore it, visualize it, right? Then there's a math part of it in terms of what are the quantitative techniques that are applicable for a certain problem. Does it make sense to apply that technique? Because at the end of the day, if there's no business impact, nobody wants to develop a big complex neural network, right? Why should you do that? Or for that matter, implement a logistic regression if it's not going to yield the business benefits. But the fact of the matter is, there is a lot of cases where applying such techniques is going to give you much better results, right? So bring in the math part of it. And of course, there's a technology angle in the sense, at the end of the day, all this has to get delivered through a technology platform, right? Be it a web interface, mobile application, right? Embedded in classical ERP type of applications, right? So all these, but technology plays a big role in terms of getting all this to the end user, right? And we also again have experienced this in multiple ways. When you order from Swiggy, right? There is an analytic thing that's going behind the scenes, but it all gets delivered in a very nice, seamless way on your mobile device. You look at a recommendation system on a Flipkart or an Amazon, that same thing that's happening. There is a very complex recommender system that's running, but at the end of the day, it presents you a very nice way of saying, if you bought this, you might be interested in buying this also, right? So technology is also fairly critical. At the end of the day, if you bring all these things together in the proper way, the appropriate manner, you're going to deliver good actionable insights for organizations, right? So that's the bottom line. I'll not go into the details here, but a quick look at, if you look at the business part of it, use case formulation becomes very important, right? What kind of use cases are there in terms of for data-driven decision making? You're talking about now, yes, you have run an algorithm, you've got an output. How do you really interpret it in a business context, right? It's not, the business is really not interested in your AUC metric or an R squared metric. At the end of the day, they are saying, with this metric, what are you helping me? Lower cost, increase revenue, increase customer satisfaction, right? So how do you interpret the output of your data science pipeline into a business decision making pipeline, right? So that's what the whole interpretability aspect of it is all about. And of course, domain expertise in specific cases. Data acquisition, how do you acquire the data, right? Data exploration, visualization, right? And data pre-processing. Math and the quant part of it is understand the algorithms at an intuitive level. What does it do, right? Select the right techniques for the right kind of problems and evaluating the output of algorithms, right? By now you must have realized running the algorithm is no big deal, right? It's just one line of code in a Python or R, and in many cases it's a GUI interface also. But really understanding what the output of that particular algorithm is and trying to compare, right? Using cross-validation and different other different techniques, what makes the algorithm powerful, right? So evaluating is extremely important. The tech part of it is about understanding the IT ecosystem, data engineering and architecture. How do you create, data is somewhere there, algorithm is here, how do you kind of bring these two together in the most seamless way? Because something will require real-time processing, something is batch-oriented thing is fine, right? Something will require so much of data that you need a big data infrastructure, right? You need to scale on the cloud. So there are many different aspects to building that data pipeline, right? And of course, software engineering, SDLC, and I see a lot of people from the IT world. So that way you will understand the software engineering principles, the SDLC, how do you run a project, how do you test, verify, validate. All those are very important things even from an analytics standpoint, right? So with that, so this is a mind map that I have created, right? So it is available free on the web. You can take a look at it at your convenience, but this will give you a complete perspective of what are all the different areas within, when people say analytics, right? There is a business aspect to it. There's a complete data. So I do cover data management, reporting, etc., because I've kind of lived that world for a long time. But the focus of this talk, and one which makes the whole data science very interesting, is the quantitative techniques. What kind of math related techniques are going to apply on data and why, right? That's a secret sauce in some sense, and that's extremely interesting. So we'll focus on that. So that is also covered. So and where this kind of a map helps you is to fit it into a context. So if you know, okay, there is this deep learning somebody is talking about as convolutional neural network, right? You might not know the underlying techniques behind it, but if you can search for this in the map, at least you will know where it kind of fits in. It fits into this space, this area, and this is what it's going to be used for. That is where you start, and then depending on whether you get that opportunity in your work life or your own interest, you can start delving into the details, right? So I'll leave that thought with you, but this is a resource that's available on the web. It's just a mind map, right? You can keep clicking and then figuring out. You can also search for specific terms and things like that. Okay, we'll come back to this. I'll probably show you this towards the end. Okay, so what's the real problem? Okay, it's great that there's a digital shift, a lot of problems getting solved and things like that. You guys are learning some of these techniques. So what's the real problem with the quantitative side of data science? The real problem to me is this. There are just too many things, right? There are just so many different techniques, and every day some new things keep coming up, right? And it's not just structured data, it's unstructured data, semi-structured data. So I mean, how do you make sense of all this world? Because you still have to navigate through this. At the end of the day, when you're in a position where you'll have to apply an analytical technique, right? You would probably be given a problem statement, right? You'll have probably tons of data, correct? Now, how do you go from there to really say, for this problem, these are some of the options that you have in terms of applying that. These are some 5 techniques that are possible here. And then how do you go from there to really say this technique is what makes sense? And not only that, once you apply the technique, you need to interpret the output in a business context. So it's not a trivial job, right? If you really take that whole pipeline, it's not a trivial job to really go from just a problem statement and data all the way up to a business impact kind of a situation. So how do you navigate through this space is what the focus is going to be. And the way I found out to be the easiest way to do it is to just divide it into categories, right? So in my mind, there are 10 plus 1. I say 10 plus 1 for a certain reason, right? So I said, okay, how do I make sense of this, right? And there is a certain flow that I kind of thought about it. This is again my own personal way of thinking about it. Some of it could resonate with you. It might be applicable from your context also. But I'll just explain what the flow is. At the end of the day, every slide is going to have these two parts. On the left side is the navigation, right? What are all the decision variables? At the end of that is basically the category. Okay, and we'll try and debate a little bit on that category. On the right side are some of the details around it. So that's where the jargon will probably come in about the different techniques and stuff like that. Again, don't worry too much about it, but it's good to know, right? Okay, so and the navigation, if you understand one, it's very similar in the other things also. So I'll spend a little bit more time on the first slide and I'll kind of rush through the other slides, right? Or go a little faster. So the first question, right, which is important to ask yourself when you're faced with a data science problem is the focus on the process or on the data, right? This is a question that many people skip. And what I mean by that is, in a classical machine learning sense, what happens is you're handed a data set, correct? And said, here is the data. Forget about the data generation process. It doesn't matter to you in some sense. Here is the data. Kind of go ahead and do all the things with data, correct? So the focus on such an analysis is really on the data, correct? But there are many different problems where the focus is on the process, which means what is that process that generated that data, correct? Now, as part of this talk, I will not spend too much time on the process part of it. I have one slide towards the end that talks about process mining and stuff like that. But I feel it's very important to ask this question because, for example, if the whole problem is about understanding the bottlenecks in a process, right? Machine learning can't answer it for you, correct? If the question is about what is the golden path in the process, how are people deviating from the norm or from the actual process which has to get implemented, there is no way machine learning, logistic regression, neural networks can't answer that question. So if the focus is on the process, you need a different kind of technique, right? But we will start with the focus is on data. Okay, if the focus is on data, which is what bulk of the slides will be. Again, there are a whole range of techniques that are there. Then the second question that you ask yourself is, what is the type of data, right? And the good thing there is, there are only three fundamental types of data, right? And I'm saying type of data from a more structure rather than from all the ratio, ordinal data, interval data, which you guys might have learned. This is about, is it structured data? Is it semi-structured data? Is it unstructured data? Correct? Structured data is very easy for all of us to understand because many of us have dealt with tables, right, in databases and things like that. Rows, columns, clear data types. You know, by looking at that column, you know what data type it is. You know the type of data. Everything is wonderfully organized. You have metadata for those columns. So you kind of, by looking at it, you understand what the data actually means at some level. What is that? So that's structured data, which is what bulk of those IT systems have really accumulated and stored. Correct? Now, unstructured is also easy for us to understand, though we haven't dealt with it in probably an organizational context, right? Some of you might have if you have worked in content management systems and all that, but most of you might not. And so unstructured data is also fairly easy to understand. It's about images, text, where there's no structure to data. You really can't put it into a schema and things like that and clearly define what this is, unless other than saying that it is a mass of, it's a wall of text, right? Or it's a bunch of images, or it is audio files, speech files, which does not have structure to it. At the start, of course, you need to translate it to some structure over a period of time, but when you're getting that data, it's all unstructured, correct? Semi-structured is a little confusing. Can anybody tell me what semi-structured data is, and in your experience, you've come across some semi-structured data? Even an Excel sheet in some senses, I would say semi-structured data, right? Because you still have to infer the column by looking at the column names, right? I mean, you'll have to understand what the data type is by looking at those column names and figuring out what the whole thing is. So semi-structured data is something like you have the ability to get to that structure, but it's not straightforward, right? There is some clue as to the structure of the data, but you still need to put some kind of a thought to understand what the data type is. Can I interpret it as a date or an integer or a float, right? So it's not strictly defined, right? And why it becomes semi-structured data is becoming a lot more interesting is because of all the IoT stuff that's coming in, right? Any sensor data that is coming to you is in some sense semi-structured, right? It will have a decent structure to it, but then you still have to discern that structure by looking at, for example, there was a project that we did for an automobile company, the sensor data that's coming in from the cars, right? So essentially the sensor captures everything about how the car was driven, right? The pedal position, acceleration, engine temperature, oil temperature, ignition, when was it on, all kinds of stuff. It's all present there, right? There's a series of vectors, there is a scalar variable and all that. But by just looking at that data, you won't know what it is. You don't know what the first column is, how is pedal position, what are those 10 numbers right up front, nobody knows. You need to have certain level of expertise. Here in this case, you talk to a domain expert to say, okay, how does it really capture, right? And the moment somebody gives you that clue, you say, okay, the first 10 numbers mean the pedal position, the second 5 numbers mean the engine temperature, right? So you can get to the structure, but it needs a certain level of processing, right? And IoT devices, everything emits on semi-structured data. So you need to have figure out a way in terms of getting to that structure, right? Okay, so I spent quite a bit of time. And so, okay, next, what is the volume of data? I think volume of data plays a big role, right? So for now, I'm saying, at least for the purpose of this slide, just for our understanding, we are saying it's not web scale data, right? We are not talking about a Google or a Facebook. We are talking about probably in the gigabytes, terabytes range, right? So I'm not talking really web scale data. Okay, I have a category which talks about web scale. So your focus is on data. We are talking about structured data in this particular case. It is not web scale data. Then you ask a question, is it time series data, right? I guess you guys have done a time series forecasting class, right? And why I'm saying time series, not time series, because the kind of techniques that you apply is again quite different. Treating a data set, if it is a time series, as a non-time series and trying to apply it will just give you garbage, right? As simple as randomizing, right? You can't randomize your data set because there is a pattern, there is a time component or a temporal component to it, correct? So assuming that it is not time series, so the answer to that question is no, it's not time series data. Then the next question you ask yourself is, does it have a label or a dependent variable, right? The moment you say yes, it has a dependent variable, then you're coming to the first category, which is probably the most simplest, and in fact, there are a lot of applications of this category. I say simplest not in the sense of belittling it. There's still a lot of applications, but this is one area which is fairly well understood, right? Which is machine learning, supervised machine learning on structured data. All of you understand this, the supervised machine learning on the structured data part of it, which is, and the next question that you ask yourself is the dependent variable continuous or categorical, correct? If it's continuous, you're talking regression. If it is categorical, you're talking logistic regression. Classification, logistic regression being an implementation of it, correct? So I'll just quickly go through this one fairly simple thing, but if you keep this in mind, I think it makes a lot of things easier when you get to the other categories. So the focus is on data. Then you ask yourself a question, what type of data? You're saying it's structured data. Then you're coming down to saying, okay, is it web scale? Probably not web scale at this point in time. Is it time series? The answer to that is no. So it's not a time series data. Then you ask yourself the question, does it have a label or a dependent variable? The answer is an S. And then you ask yourself, is that dependent variable a categorical or a continuous variable? If it's continuous, you go the path of regression techniques. If it's categorical, you go through the path of the classification techniques. Right? So this is category 1 for you. Category 1 might appear straightforward, but still there is a lot of different nuances towards how do you address this problem. Again, some of this you might have already come across and all that. So how do you do exploratory data analysis? That is an area by itself, right? How do you look at the data? How do you organize your data? And the whole thing about data pre-processing, outlier identification. How do you treat missing data? Because one of the biggest thing with all these different techniques is it is a situation where you put garbage in, you will get some fantastic, you're probably better off not implementing data science and machine learning in some cases, right? Because your gut decision probably might be much better. But if you feed in the right kind of data and the algorithms can actually get the signals in that data, you can get some fantastic results. Right? So data pre-processing talks about outliers, missing data, variable transformations, right? Then there's a whole aspect of feature selection, dimensionality reduction. Okay, so essentially I'll give you a quick thing. Obviously, people will talk to you more in detail. So the whole idea behind ensembles is that you're not just getting, so if you look at a logistic regression, right, and what is called as a parametric algorithm, right? Logistic regression has a linear thing to it, right? And then you basically, the whole idea of logistic regression is to estimate the parameters. By looking at the observed data, you basically estimate your different coefficients or the different weights, right, to the individual features, correct? And so the mathematical equation is set, correct? You don't have the liberty of looking at the whole hypothesis space, but your equation is kind of set. An easier example would be a linear regression, right? Y equals your whatever, B0, B1, X1, B2, X2. And then all you're doing as part of the whole thing is figuring out what does B0, B1, B2s are, correct? So that's linear regression. Logistic regression is similar. And so you have some of these parametric algorithms. Ensembles is about bringing multiple things together. So you have a decision tree, which is an individual algorithm. You kind of build multiple trees to estimate the output, right? And that is basically becomes a random forest. Right? Of course, I'm talking at a very high level. There are nuances to it on how you really combine the trees, what you look for and things like that. But the whole idea of ensembles is you take multiple weak learners, you combine them together, it makes for a very strong learner. Okay? So bagging about combining multiple algorithms, boosting, there is a different technique, but the essence is very similar, right? Take multiple things together, each one predicts something, and then you kind of combine all that together to give your final predictions. Correct? Okay, so those are the ensembles. Parametric, non-parametric I just spoke about. Algorithms can be linear, non-linear type of algorithms, right? Cross-validation, right, is extremely important in terms of evaluating the output. Then hyperparameter tuning. Do you guys know what hyperparameter tuning is? So every algorithm, right, has parameters associated with it, correct? So it will be the number of trees in a decision tree. That's one parameter, right? How do you know how many trees to build? Right? Is it 10 trees, 25 trees, 50 trees, 100 trees? Right? And similarly, if you look at some of the random forests, there'll be like 25 different knobs that you can actually adjust, right, to get you great performance. So hyperparameter tuning is a way by which you can actually get to the best parameters for that particular problem. Right? So what people do is they do a search and say, okay, I will take the different parameters, put them in a grid, and then try and solve the problem and see whether I get better results, right? And once it gives the best result is the parameter that I want to go with, right? So there are ways by which you can actually get to the actual parameter that will give you the best performance, right? That's what is called as hyperparameter tuning. And of course, at the end of the day, you predict on the test set. You have a model that is built, right, on your training data, correct? You cross-validated, you have looked at either ensemble, standalone, all that you have done. And at the end of the day, you have to predict this use this to predict on test data, right? So have you guys done something in terms of training a model, predicting it on a test data set and all that? Okay, so there are some interesting things there. I mean, it might look a little simple, but as simple as, let's say there's missing data in a column, right? And you apply the mean to basically on the training data set to say, okay, I'm basically for all the missing data, I'm going to fill it with the mean or the median. You guys must have done it, correct? Now, if you have to apply this model on the test data, you can't again do a mean computation on the test data, correct? You will have to take this mean which is done on the training data and apply that, correct? Mean is a very simple example, but if you use one-hot encoding and more complex things on your training data, you need to do the same thing on your test data. You cannot do it afresh on the test data. These are nuances which are extremely important. Again, the moment you do it on the test data separately, you're not going to get the right results, right? Category 2 is the focus is still on data. The type of data is structured. It's not web scale, not time series. It does not have a dependent variable. So you guys know what the category is? Right? Unsupervised machine learning on structured data, right? With its own set of specific techniques, right? Clustering is something that you would have heard. You would have probably even done it. K means clustering, hierarchical clustering, but it will be interesting for you to know there are probably another 25 different ways you can cluster data, right? Fairly sophisticated ways of doing clustering and identifying patterns in your data, right? But the bottom line is you're creating, so you're not predicting anything, you're just understanding the structure in your data, correct? Anomaly detection, that's one of the, we get a lot of things around, especially with respect to sensor data and all that coming in, detect anomalies, right? So the techniques by which you can actually take all the data, have algorithms like isolation forest and things like that, which will help you to detect anomalies in data, right? Recommendation systems, that's an area on its own, but again, in our daily life, we have come across many recommender systems. And there are many different techniques, right? Item collaborative filtering. So probably it makes sense for you to quickly look at some outside resources, because it's a fascinating area in terms of how do you do recommendations, right? How do you look at user similarity? How do you look at item similarity, right? And then how do you kind of correlate one over the other and give appropriate recommendations to people? And it's a great area by itself, right? We spoke about the dimensionality reduction like PCA. PCA you must have all heard. Have you heard of TSNE? TSNE is again a very nice way of reducing dimensionality, and you can get it in a very visual context. Very high dimensional data, you can get it into a more interpretable visual context, right? That's TSNE. So this is unsupervised machine learning on structured data. So exploratory data analysis is still important. You need to understand the structure within your data. Clustering, k-means, hierarchical, many others. Anomaly detection is isolation forest, LOF, I forgot what the expansion is. Recommenders, content-based, collaborative filtering, hybrids. There is another thing called self-organizing maps, SOMs, right, which is basically a little more advanced way of doing clustering, right, and also identifying outliers, right. Okay. So let's move to the third category, right. By now you must have guessed the whole logic, right. Focuses on data. Type of data is structured, not web scale. Yes, it is a time series, right? The moment you come to time series, your classical things might not work, right? Or it will not work in the same way as you used to do for a linear regression or logistic regression, even for an ensemble scenario, right? And typically time series has a label associated with it, right? You're predicting something. More often than not, it's a continuous variable. And why time series is extremely interesting, important from a business context is that's probably the first problem which will be posed by any company. Can I forecast demand, right? Can I forecast sales? Because once I forecast things better, and forecasting is not new. Forecasting has been done by people for many years, right? So when we work with companies, what happens typically is they say we already are having forecast. Okay, we've been doing it 25 years. Some models has been running for a long time. Typically it's developed in SaaS mostly, but they are not getting accurate forecast. They are not getting granular forecast, right? Because the techniques have changed drastically from what used to happen, whatever, 15, 20, 10 years back, right? So there's always a requirement for companies to do better forecasting in multiple different things. If you really look at it, forecasting is something that it's very wide, right? Sales forecasting is one part of it. You can do employee related forecasting. You can do infrastructure forecasting, right? So the thing that we do for Facebook, right, is basically about IT infrastructure forecasting. Right? They need to know how many laptops they need, how many servers they need, right, for them to plan the whole thing appropriately. That's a classic forecasting, and it's a fairly complex problem. You're looking at demand, you're looking at supply, you're matching the two, right? So there are specific techniques, and good that you guys have gone through a time series forecasting thing. But personally, to me, I find time series forecasting to be the most difficult in some sense, right? Because it might appear to be very straightforward, but at the end of the day, you never get good forecasts for some reason. At least probably just me, but and there are specific fundamentals, so to say, of understanding a time series before you can start modeling on top of it. So in your course, again, you must have heard about stationary and non-stationary time series. You guys have gone through that, right? So that took quite a while for me to understand, right? And how do you stationarize a time series? Why is it important? And things like that. What are the techniques by which you could do that? Right? How do you decompose a time series? Look at your trend, look at your levels, right? Look at the noise, what is called as white noise and things like that. And how do you do autocorrelation plots, ACF, PACF? How do you detect the differencing? All that are very interesting techniques which you will not find in a typical supervised machine learning problem, correct? Of course, feature engineering is also, it's very interesting in a time series scenario on how much of moving averages and lags that you want to calculate, right, in order to get better forecast, right? And building time series forecasting models, the classical way of doing it is ARIMA or a Holt Winters and things like that. But more recently, there are a lot of deep learning techniques that are coming in, right? So for example, something called recurrent neural networks right now gives you probably the best results when it comes to time series forecasting. It's a deep learning model. It is used for sequence prediction problems typically. And time series is nothing but a sequence prediction problem, right? You have a sequence, you're trying to predict the next sequence, right? It might be for 12 months or the most immediate data point, whatever that might be, but you're still predicting a sequence, Yeah, so that's basically, so what I also have, I'll probably show it towards the end, is for each of these categories, I have some sample illustrative code. Of course, it's written in Python because that's what I'm comfortable with. It's part of my GitHub repository, right? Not probably the best possible code, but it'll give you an idea if you want to get started in an area, right? How do you really get started? There could be some template code, which I'll show you towards the end, okay? So, and that code which is there in my GitHub, basically uses ARIMA-based time series forecasting, right? Category 4 focuses on data, but now the data is unstructured, right? And I'm kind of bucketing semi-structured under the structured thing, so I don't have a separate category for it because there's one extra step to make it structured. But the real big difference is unstructured data. The moment you say unstructured data, you're talking text and things like that. Volume of data, probably not web scale at this point in time, has label dependent variables. Now, if the answer is yes, then you're talking about supervised machine learning on unstructured data, right? The most simplest classical use case is spam detection, right? How do you detect spam in emails, right? There is text, so you need to understand the text, structure the text, right? But at the end of the day, you're still predicting whether that email is a spam or a ham, correct? That's the easiest example, but something like sentiment analysis, image classification, all that falls into the whole supervised machine learning on the unstructured data space, right? Type of unstructured data, it gets very interesting here because depending on the type of unstructured data, there are different techniques again, right? Different type or category of techniques. So if it is text, it's all about natural language processing, right? Have you guys done anything on text analytics, natural language processing? You've done it? Okay. You do it as part of your daily job, is it? As part of your work. Okay. I mean, you would appreciate the amount of, one, it's extremely interesting. And right now we're just scratching the surface of the whole thing, correct? We probably use a bag of words model. You take the terms, vectorize it, and you basically use it for models. But there are very sophisticated techniques that are out there, correct? We'll talk about that a little bit. Again, it might appear as jargon if you haven't done text analytics, NLP, but it's good to know. If you're talking about images, now you're talking a bunch of images. If you looked at Kaggle and things like that, a lot of competitions now is about image classification, correct? I think there was a recent one where that was actually a sound thing. Using the sound that is emitted, can you detect a whale or not, right? That was, I think, one of the recent things. But there have been many, from the pictures, can you detect cats and dogs is a classic learning problem in Kaggle. But images is becoming very, very big nowadays, right? Even in a business context, because nobody's even touched those images. But now people are starting to think if I can actually get interesting insights from images, now the world is anyway, I mean, we keep clicking so many photographs, so many things, and there are so many pictures on your mobile phone. Just imagine for an organization, there are just so many images that are there. So one problem that we are working on, just to kind of motivate you in this direction, is, so we work for Pepsi, and the assembly line, the sensor basically takes a lot of photographs, right? And then what they really want to do is, using the photographs, can you detect defects, right? Bunch of photographs, and they actually have labels associated with, says defects, not defects. And then once you train your CNN or your convolutional neural network for the new images coming, can you detect an image or not? Can you detect a defect or not, right? Now, you can expand it in multiple different ways in your own customer situation, in your own whatever you're working on. I think it'll be good to figure out whether there is text that is involved. Can I do things better, or can I get some insights out of text? Images, if you're dealing in some way with images and stuff like that, probably there is a wealth of information out there, right? And if it's, so in terms of types of unstructured data, we spoke about text and images in a kind of a standalone manner, but speech is text having a temporal nature, right? Or there is a sequence associated with it, right? Audio, speech, videos, for example. Videos is nothing but images in a sequence, correct? And for that, there are different techniques, and the state of the art is something called recurrent neural networks, or RNNs, right? Which is useful for sequence prediction. So this category is all about, you're still doing supervised machine learning, so all those other techniques still apply, but you need to figure out a way to take all this unstructured data, convert it in some way to a structural form, and then start applying the different techniques on top of it, right? So NLP is probably the most interesting because there is text. People have already started doing quite a bit with text, and now you can do a lot of things with it, fairly sophisticated things with text. So that is where the maximum activity has been in terms of using text for predictions and classifications. Convolutional neural networks and RNNs is used in a big way in specific industries as of now, but this is also going to become mainstream because images and all the, this has not been touched at all by organizations till now. So there's a lot of opportunities out there, right? Have you guys done neural networks, artificial neural networks? Oh, you guys started doing it, okay. Which is good. So ANN is the basis for many of these different things, right? But there are very sophisticated architectures, right, that make a CNN different from a classic ANN, and also from recurrent neural networks have a memory associated with it, makes it different, right? Okay, so that is, okay, this is a brief detour. Let me anyway go through it. So why is text so interesting for people is basically because of this, right? One, there is a lot of unstructured text. What they say is 80% of the organization is unstructured data. People haven't really tapped into it, so every organization wants to do something with it, right? If somebody is, some of you is from the content management side, you would have seen when organizations implement CMS, they throw in a whole lot of documents into it, but all the best they will do is probably search through it, keyword search. There is really nothing that they get out of CMS other than probably search, right? Which is important in its own way, but now with this kind of techniques available, you can actually extract a lot more insights from text. And text typically packs a lot of information within a short window, right? So if you look at this particular piece of text, it captures issues, product, urgency, organization, customer. There's typically a lot of information available within text, right? And text analytics is the foundation for any higher levels. If we talk about artificial intelligence and all that, unless you can process text, speech, audio and things like that, you really can't build intelligent agents, right? Because that's a very important part of how we live our daily lives, right? Text is important. We listen to words, make sense out of it, get the context from these words, sentences and things like that. Again, this slide I'll rush through, but just especially for a person who has already been in NLP to know, there are a whole lot of techniques and fairly sophisticated ones, extremely interesting in terms of the power of these techniques. So at the end of the day, what you want to do with the text corpus is basically four things. One, you want to convert text to some numerical output so that you can use standard machine learning algorithms, right? Which is where count vectorizers, and you can vectorize text and give a number to that word, right? What is called as a bag of words model. And then you can use it for any kind of a machine learning prediction. So that's one thing that you would typically do. You can extract content from individual documents in the corpus. So you give a corpus and say, tell me whether the names of organizations which is there in this corpus, correct? Or names of people, right? All this parts of speech tagging, entity extraction, right? All that is also you can do with, you will try and do with text. Then dimensionality reduction, right? You want to reduce the dimensionality because if every word becomes a dimension, there are just millions of dimensions, which is very untractable. And then extract relationships between words and documents in the corpus. So you have again a whole lot of techniques, of which the most famous one, if people have heard, probably you would have heard of it, is word2vec, right? So word2vec is how Google runs its search right now. Okay, word2vec is convert word to individual vectors, right? This is a topic on its own, but good to know that there are, I think it'll be good to know that these are the different techniques, state of the art in terms of handling text, right? And this is a ocean by itself. But if anybody is interested, this is a great area to be in because I think I would say the next 5 years there's going to be a lot of text-based analysis in multiple forms and shapes. They're already seeing seeing organizations start delving into it a lot more, right? But suffice for you to understand, given a body of text, there are ways by which you can make it structured. There are ways by which you can extract meaning out of it, right? You can extract insights out of it. You can understand the semantic equivalence, right? Which means what is this word equivalent to, right? So the most classic example people say is, given a corpus of text, if you use word2vec, right, which is basically what is called as word algebra, is that then you can actually have algebraic statement saying king minus man plus women, right? Women gives you queen, right? You can actually start doing those kinds of exercise, what is called as word algebra with text itself. And why is that possible? Because everything is codified as a vector. There is a way by which you can convert each piece of word into a vector, and the moment it's a vector, you can do all sorts of mathematical manipulations on top of it, right? If not anything else, just go and look at word algebra, try and look at some videos. You will find it extremely fascinating on how you can actually do this with words, right? Okay, so let me just quickly move on. I think I have another 20. Okay, category 5. So we have another 5 categories to cover. So focus is still on data. It is unstructured data, not web scale, no label, right? Which means you're doing unsupervised machine learning on unstructured data, right? Which is, again, you use the same type of techniques in some sense, but here you don't have any dependent variable. You're just trying to understand the structure within text, or you're trying to understand the structure within the images, or you're trying to understand the structure within your whatever audio and things like that, right? And I've put question marks there because I don't know whether CNNs and RNs are still applicable in this area. I haven't done much investigation into that space, but I know for a fact there's a lot of NLP that is used for just unsupervised machine learning, right? So some of the topic modeling and things like that actually falls into that category, right? You have a bunch of text, can you divide it into specific topics, right? Full range of NLP can be utilized, what you saw on the previous slide, right? A part of speech tagging, topic models, word embeddings and things like that. There is something called GANs, right? Which is, this is all generative networks. There are also neural networks that generate new things. Neural networks write movie scripts. In fact, that movie script, there's a famous example of a movie script written by a neural network that won some, whatever, 5th prize or 6th prize in a particular film festival, right? There are things that create new art. There are neural networks that create new music. So this is one area where neural networks are becoming generative, right? By training the neural network with a bunch of, let's say, Picasso paintings, it can actually generate new types of paintings that can be, that is very similar to the previous ones that it has seen, right? There are fairly advanced, I haven't seen this in a more business context, but these are some interesting developments that are happening, which will come mainstream probably over a period of time. Yeah, GANS is generative models, right? So it's, okay, generative adversarial networks is, so examples are something like, so the moment you're generating stuff, which means generating new art, generating new music. And the most classic example is generating movie scripts. So what these guys did was they fed a bunch of Hollywood scripts to a neural network. It looked at all the patterns and things like that. It actually, the output of the neural network was a new piece of movie script, right? On which they actually got in actors to act on that script, and that won some award and stuff. It's a movie called Sunshine. And so there are neural networks that are coming in which are not only just discerning patterns to kind of predict whatever the test data is, but it is actually generating new types of content. That's the whole, and it's called adversarial because there are two neural networks that work together to make these things happen. Right? One neural network generates it, the other neural network verifies that whatever is generated is good enough. Right? And so you have two neural networks working in conjunction. I'm quickly moving on. So category 6. Category 6 is essentially, it's what is called as reinforcement learning. If you look at machine learning is divided into 3 categories, right? Supervised machine learning, unsupervised machine learning, which is what we saw earlier, and there is this whole area called reinforcement learning, right? So what happens here is, it is structured, unstructured data. Typically reinforcement learning would involve both, but it can also work with structured or unstructured data. But really the difference here is the feedback from the environment, right? And the simplest way to understand this, something like a game, right? And so a lot of work in reinforcement learning happens on game environments, right? So when you play a game, right, a Pac-Man or even complicated games like Doom and stuff like that, you take an action, but there is also action coming in from, in this case, a particular game, but then think of it like an environment, right? So the environment gives you certain kind of a response, and at the end of the day, you get some delayed feedback, right? Either you win the game, lose the game, you score so many points, all that is possible, correct? So how do you really do machine learning, or how do you make an agent learn in that context? Where the agent takes an action, there is feedback coming from the environment, right? And this feedback is not the ultimate objective. The ultimate objective is winning the game, which will happen probably after 3 levels, 5 levels, 10 levels, whatever that might be, right? How do you take that feedback and take the next best action, right? So if you really correlate it, that is what artificial intelligence is, right? If you want to have a robot, right, move around this place, it basically has to figure out, should I take the right or the left right now? Am I hitting an obstacle? If I'm hitting an obstacle, how do I take back and how do I move forward? So this is all something you have to take an action, relate to the feedback and take a next best action, right? And at the end of the day, you probably achieve your goal of probably, if it's a robot, it has to probably cross this and then reach to the other end, right? But it can be fairly sophisticated for many other different types of situations. So that's the whole area called reinforcement learning. More than a business context, I think this is where artificial intelligence kind of comes in, right? How do you develop intelligent agents that can take actions, right? Not with, so when I say delayed feedback, right, just to clarify that a little bit, if you look at supervised machine learning, you're getting immediate feedback, right? You have a label. So you do prediction, you have a label which tells you this prediction is so far away from the actual one, correct? So you get immediate feedback on your single row of data, correct? Whereas in the case of reinforcement learning, you're not getting that immediate feedback, you're going to get delayed feedback. Take any game, chess for example. You play a move, opponent plays a move, but at the end of the day, the feedback is about winning or losing the game, which comes much, much later, right? So how does an agent evaluate the position at every single point in time and take the next best action is what the whole reinforcement learning area is all about, right? The good news is there are algorithms, there are again, if you're a Python guy, R guy, you can implement it on your laptop once you go back to your rooms or homes, right? It probably take 3 hours to implement a reinforcement learning algorithm. So that is not the limitation anymore, right? There is code available. In fact, in my GitHub, reinforcement probably haven't put in a piece of code, but it's readily available, right? I will add that soon. And there are all these autonomous cars where there's a lot of talk. That's all about reinforcement learning and artificial intelligence, right? Think of it, that's the other end of the spectrum. A car has to kind of drive itself and it's getting feedback from the environment in many different ways. There is wind, rain, right? Obstacles, pedestrians, signals, right? Just imagine the complexity out there. And it's happening, right? It's just a matter of time before it kind of spreads all over the world. Right? Again, I've just given some terms so I'll leave the presentation with you. So at least some of these terms, you can take a look at it and see what are some of those techniques that are out there. And these are all not static. These areas keep moving. These are rapidly evolving areas. So a month down the line, there'll be some new algorithms and new implementations that have come in. Correct? Okay, AlphaGo platforms. Okay, that's basically what the reinforcement learning is. I'm not going to spend too much time, but I just want to introduce this topic called Bayesian machine learning, because this is again not something which is very, I would say, thought about. But if you look at machine learning, the biggest problem with the machine learning output in a business context is you give a prediction, right? You give what is called as a most likelihood estimate, right? You say, here is a bunch of training data and I'm predicting a single variable for you or a single prediction for you. Now, in certain contexts, that is okay, but in certain other contexts, that's not acceptable because you don't know the uncertainty around those predictions, correct? So, just to give you an example, let's say this is about detecting something in a patient, right? To verify whether you'll have to have a surgery on the patient or not, right? Let's say that is what your machine learning models are used for, right? Just imagine from a doctor's standpoint, you're giving a logistic regression kind of a prediction and saying there is a probability of 0.8, right? So whether the particular disease is there or not, right? You really can't the doctor cannot take a decision just with that point estimate, right? What you need is a level of uncertainty in the estimate, right? Level of uncertainty comes from the fact that you give a prediction and say, yes, this is the most likelihood prediction, but all the other types of things are also possible in a range, correct? So that is what Bayesian machine learning helps you to do. Bayesian machine learning is all about giving not only the predictions, it also gives you the uncertainty around the predictions. And it is not a new area in the sense that you have done linear regression, there is Bayesian linear regression. You have done logistic regression, there is Bayesian logistic regression, right? So it's not a completely new area by itself, but the thought process is different, right? I just leave that with you guys because from a business standpoint, uncertainty is extremely important for a business guy to take a decision and tell a stakeholder, you know what, I'm taking this decision, but this is how uncertain it is, correct? Rather than giving one particular estimate. So personally, I feel this is a great area to explore because at the end of the day, if you really want your business to take a decision, you need to provide them a level of uncertainty in your estimate. Otherwise, they are not going to trust you, correct? So again, there are multiple packages, multiple ways of doing this. Again, if you have the time, please do check on some simple thing around, okay, you know what a linear regression is, see how Bayesian linear regression is different and what output does it provide So that you're comfortable about the fact that, okay, now this is something over and above a classic machine learning kind of a situation, right? So that I put it as category 7, and I do have a notebook in my GitHub where you can quickly take a look at it in terms of what that is all about. Right? Category 8 is, okay, now we have done supervised, unsupervised machine learning and reinforcement. We have looked at it. We looked at text, images, all that. But what if the data is web scale, correct? You can do certain things on your laptop or with probably with enough memory, enough cores on your machine. But what if you're talking really web scale data, terabytes of information, correct? So how do you scale machine learning? So scalable machine learning is an area by itself, right? Where you're talking about things like Spark, right? Big data, cloud, all those things come together when you're talking about scalable machine learning. The moment you say, yes, I can do things on one machine for a certain volume of data, but as it scales up and you're looking at web scale data, the same thing will not hold good, right? So how do you scale? How do you use a Spark in a kind of a, so bottom line is, again, I recently came across this thing called H2O, right? That's also built ground up for scalable machine learning, right? And this is an area which will again expand rapidly because every organization now wants to, for most of the work that we do, again, cloud is a de facto thing. We don't do anything on premise right now because just the volume of data is just so huge, right? And just the car sensor data I was talking about, you're talking about every single car in 158 countries, and the volume of data is just so huge you can't really put it on anything. So you put it on, we used a platform called Databricks, which is essentially Spark on the cloud, right? And use tons of machines to process all that data, right? And the good part is it's not costly. You're going to use it for a certain period of time. Yes, you're going to use that power for a short period, but it's very, compared to the benefits that you can get out of it, the cost is not prohibitive at all, right? So big data, cloud is going to play a big role because now it's all about scalable machine learning. How do you scale across computers? And the good part is, in order to learn how this works, you don't need a cluster of computers. You can still do it on your laptop, right? So you can write a piece of Spark code, again, linear regression, logistic regression, decision trees, whatever that might be. Run it on your machine, okay? See how it works, etc. The same code essentially works for thousands of machines in a cluster. You don't have to even change a single line of code because there is something called a Spark session context which abstracts the distributed nature of Spark. You don't have to know anything other than knowing how to work with Spark in a machine learning context, correct? Okay. There is also this fascinating area called search. If you come across Elasticsearch, Solar and things like that, there's a lot of activity that is happening in terms of you throw in a bunch of data into a search platform, right? And it indexes everything, and on top of it you can run machine learning. You really don't need, at least people like me used to spend a lot of time creating data warehouses, right? ODS, data marts. On top of it you run certain types of reports and stuff like that. Some of these search techniques is very simple. You just have to index it into Elasticsearch, and on top of it you can run reports, you can run machine learning, you can run it straight away. You don't need to really invest time in developing schema, right? Do all that kind of stuff, right? Not that it is as simple as what I say, but potentially, right? You don't have to spend real time in building all those different platforms, right? And each layer of the platform adds to latency, adds to complexity and things like that, right? So this is again a fascinating area in terms of enterprise search. Okay, so that's scalable machine learning. That's category 8. I'm not going to talk about this slide. I'll leave it with you on how do you make sense out of big data. Again, if you look at any big data, if you look at the big data 2017 picture, the landscape, it has some 200 odd technologies, platforms, techniques. You get like totally overwhelmed with it. But the way to make sense is to divide again into some areas, saying, okay, distributed storage, distributed processing, SQL access, machine learning, right? Some categories, and learn certain techniques around it so that, again, over a period of time, if it's really required, you can get into the details of each of those technologies, right? But big data is there. It is there for, especially from the analytical context, it is going to be big. It is already kind of getting into almost every single aspect of machine learning, right? Okay, so that's big data. Category 9 is, category 9 is optimization, right? It's one thing to have predictions, right? You can give out predictions, but if you put it in a business context, the business has constraints, right? It's one thing to say there is the demand for your product is going to be whatever, so many units, 100,000 units, right? But the business will have constraints in terms of, okay, how much can I really produce, right? At what cost, right? So there is a lot of constraints around how much of those predictions can I actually fulfill, correct? So at the end of the day, every analytics I wouldn't say many analytics problems have to end with an optimization thing, because if you're putting it in a business context, the business is going to say predictions are fine, but these are the kind of constraints that I have, right? The most classic case of optimization that we do is like what is called as media mix modeling, right? If somebody has done that, the marketing manager basically has this problem of how much money should I allocate to different channels, correct? So you could have some regression and all predicting, saying this is the kind of money that you have to invest to get the maximum output, right? Or this is the money you can invest. But there are going to be constraints that they cannot take all the money out of, let's say, a TV ad, right? They still have to spend something on TV ads because they can't really move away from that medium completely, right? So there are going to be constraints in that problem. So finally you'll have to solve an optimization problem there, right? Minimum, maximum. Have you heard of optimization? You guys have heard of it. So I'm sure you understand the language that I'm speaking. At the end of the day, right, you have to put in those decision variables, the constraints, and solve either to maximize or minimize, as the case might be. And the good thing here is if you combine machine learning with optimization, it makes for a very strong output, right? Because predictions are the output of your good machine learning algorithms that you've already developed, evaluated, and you're also kind of putting it into a business context, right? And it need not be in a business context. So again, I have a piece of code which basically talks about using optimization in your daily life, right? So the example that I have, which I submitted a blog on, is in terms of, okay, if you have to really optimize on how many TED videos you've got to watch, right? You have certain amount of time, right? The TED videos are all available, which runs for a certain period. Every TED video runs for a certain number of minutes or whatever, right? If you want to say, how many TED videos should I watch for the next 6 months, 1 year? I have so much time and I don't want to be overloaded with stuff. Can I use linear optimization to solve the problem? If you want to go on vacation, you have a certain number of days available, right? You have a certain budget that you have. What vacation should you take? You can use it for all kinds of problems. And of course, it's very powerful in a business setting also, right? So very relevant in a business context, many optimization methods are available, and optimization is again a very well researched topic, but the good thing is it is all available again on R, Python and things like that. So Python use a package called Pulp, which is basically a package to linear programming. I'm sure R also has got a package. But essentially, again, going back to my earlier thing, if you know what you don't know, there are going to be opportunities for you to do all those things on your laptop, right? But the key thing is to know what you don't know, right? To figure out, okay, this is one area which is interesting, word2vec. As long as you know that word2vec exists and that is used for this kind of a purpose, you don't need to know word2vec today, correct? You can learn it as and when an opportunity comes. But if you don't know that, tomorrow when somebody is asking a question, you can't even figure out what to answer that person or how do you have an intelligent conversation. That is why that breadth and understanding is important. The depth, go into it as per your requirement and the need, because going into depth across all these areas is just not humanly possible, right? The last one, the last penultimate one is machine learning in production, right? Which is about, yes, you can do all this fantastic stuff, but how do you really get it to the end users? There are a lot of questions that you have to answer to really push machine learning to production, right? So you need to understand the technology, web technology, probably you need to understand some kind of so you need to understand the IT ecosystem, answer a bunch of questions, right? Saying, okay, how frequently are you going to run the model? How are you going to get the feedback, right? To feed it into the model for you to recalibrate it. There are many aspects to running machine learning in production, right? And at the end of the day, all of us want to do that, right? We are not just learning machine learning for fun or data science for fun. We really want to implement it in a business context, and the business or anybody has to kind of take an action on it, right? So there are multiple things in terms of getting machine learning into production. The last one, I've said 10 plus 1 because this is where we are starting to think if the focus is on the process, not on the data, right? So all along we have only seen cases of you're given data or you've extracted data and you're working with data in multiple different ways. What if the whole thing is about the process, right? And typically the process data is all structured. And what I mean by process in a typical sense is purchase order, right? loan application process, right? Everything has a series of steps associated with it. And the question is basically, okay, what are the bottlenecks in my process, right? Where are the deviations in my process, right? Can I discover the process, what is called as process discovery, using all this data? And there is the area called process mining. Again, nobody talks about it in a very big way. But if you are a person who is interested more on the process side, especially if you are on the supply chain and areas like that, right, process mining is probably more important than data mining or your machine learning, because with machine learning, at least as far as I know, you can't answer questions like this, right? You need to, and this is also a fairly well researched, mathematically strong area. You have a bunch of algorithms which will tell you how to identify bottlenecks, how do you identify performance metrics, right? All types of very interesting stuff. If you are a process person, yeah, I'll just complete this. If you are a process person, check out processmining.org. That's an ocean by itself. You can just make your career just looking at process mining as a discipline. Sorry. But I just want to talk about 3 key skills that you need to acquire to be successful in the analytics space. Again, this is just my personal views. 1, business connect. Every problem, unless you're able to define it in a business context, analytics is immaterial. That's one key learning that I have. So if you are especially a hardcore technology person, which in some sense I was earlier, the biggest roadblock or the biggest thing that you have to cross is about looking everything from a business standpoint and asking the question of so what? So what if you implement this algorithm? So what if you get this kind of metrics, right? At the end of the day, how is the business going to get impacted is extremely critical in this space. Probably the whole narrative has to change in terms of people talking about, oh, this was the problem that is being tried to solve, is being tried. And so this data-driven decision making is important. So I would want to bring that up front. Again, some categories and things like that. But the key thing is there might be programmers out here who are very comfortable doing R, Python and things like that. So no problem, you can pick up your programming language of choice and go with it. But there could also be non-programmers, right? And I've seen at least people coming to me and saying, I feel left out in this whole thing, right? People talk about a lot of algorithms, but I'm not able to do it because I don't want to really sit and learn Python for now. I'm a domain expert, having invested so much time doing this. The good thing is, then I would say, please look at some of these GUI based tools, right? If you look at Microsoft Azure Machine Learning, if you guys have looked at it, it is basically a way to assemble things together. It's all GUI based. You don't even have to write a line of code, right? H2O is another very classic platform, big ML, right? These are all platforms which are completely GUI driven, right? And even if you're a programming expert, I think it'll be good to know some of these platforms because you can do things much faster, right? Especially to prototype things and quickly get some predictions and stuff like that. It's amazingly easy to do it on an Azure machine learning platform. And Azure machine learning is free, by the way, for I think up to around 10 GB of data, I think, right? So you can pretty much do all your practice, even for fairly large data sets using Azure machine learning, right? So try out Azure machine learning, try out H2O.ai, right? Fairly sophisticated algorithms, GUI based. There's something called Flow that it has. Then of course, Big ML is another platform which is very interesting. So, and I think there are quite a few others also, Naim and things like that. So this slide is basically says non-programmers need not feel left out. You can develop an intuition for all these different algorithms by using a GUI based models also. Think technology landscape is another thing. Don't get too focused on just the data science machine learning part, because at the end of the day this has to get implemented within an environment. So think technology landscape. Again, expertise is not the key thing here. If you already have expertise, great, but at least a feel in terms of, okay, how is it going to get implemented? What questions should you ask or you need to answer, right? Cloud, mobility, web technologies, embedded analytics, legacy systems, just get a feel for it. Cloud is probably the most important. If you ask me right now, in another 3 years, I don't think there'll be any analytics without the cloud. Everything will be on the cloud, because that's the power of the cloud, especially when it comes to scalable machine learning. You can prototype stuff, but in a real production setting, it's going to be there on the cloud most of the time, right? Because that's the volume of data that you're dealing with. So that's basically what I had, right? Thank you very much for your patient hearing.
In this tutorial, we have learned what is data science and what are the topics and what are the concepts comes under it. If you like the content, then please do let us know in the comment section. And also, if you want to learn more about these concepts, then please go to Great Learning Academy, where you will get almost 80 plus free courses. And after completing your course, you can claim your certificate as well. And if you want to do these courses in your mobile application, that is also possible using Great Learning app. Thank you so much.